Hi guys, today I will be discussing Compton's effect with you. This effect was given by Sir Compton and he was awarded Nobel Prize for discovering this effect. Now from beginning in the history of science there has been ambiguity whether light follows wave nature or particle nature. There has always been argument on this wave particle duality of even particles, you can talk fundamental particles. Now this Compton's effect, this supports the particle nature of light. The motive here, what we will be talking in this video, the motive is to reach to a formula which will provide us the value of change in wavelength between this scattered photon and this incident photon. Now let's discuss this experiment, what's going on here. This whole experimental system is an isolated system, and in this system what we are doing, we are taking a target particle, which in this case is electron. We incident a photon on this electron, and what we observe is that the photon scatters, the electron scatters. Okay. Now as the photon scatters, we see electron is also scattering. So initially it was having zero momentum, and after the photon strikes it, it is having some velocity. So surely we can say that this incident photon has supplied some energy to this electron on striking, and the remaining energy is with this scattered photon. So here we will get our first equation here by energy conservation. In this case, incident photon is having energy h nu, its frequency is nu, h is Planck's constant, and the scattered photon energy is h nu dash, and here the difference has been used as the kinetic energy of the scattered electron. Here I will label this momentum of electron to be P. The momentum in this case for photon will be written as its energy by C. So the scattered photon is having energy h nu dash, so its momentum is h nu dash by C. The incident photon having energy h nu, its momentum is h nu by C. Now as I said, we are discussing about the particle nature. Of light. So we can assume the photon and electron, they both are striking like two billiard balls. Now as that, or you can say point masses, so as they are striking like two point particles or billiard balls, so here as there is no external force on this system, so surely we can say that momentum will be conserved. Now this is very interesting thing. This effect also teaches us that how to conserve momentum in modern physics. The funda is same. If F external on the system, the external net force on the system is zero, initial momentum will be equal to final momentum. What changes here is the formula of that momentum for photon or for different particles. So as I said, the external net force acting on the system is zero in both the directions, in the x direction, in the y direction. I have defined the axis here, the horizontal one to be x, the vertical one to be y. So first of all, I will conserve the momentum in x direction. Now the component of momentum of scattered photon in x direction is h nu dash by c cos phi. I have assumed that the photon scattered at some angle phi, electron scattered at some angle theta, which are arbitrary. Now, so we wrote the x component of momentum of scattered photon, that is h nu dash by c, the momentum of scattered photon, and its component cos phi multiplied. Now, this is in the positive x direction, so we will have a plus sign here. Next, writing the momentum of scattered electron in x direction, that will be equal to p times, p is the momentum of scattered electron, p times cos theta. So p cos theta will be the x component of momentum of scattered electron, and the initial momentum in x direction was that possessed by incident photon. It had no component in the y direction, all of its momentum was concentrated in the x direction. So the initial momentum in x direction will be h nu by c. Similarly, h nu dash by c sin phi, the y component of scattered photon's momentum, it is in the positive direction, and next we have p sin theta, It is the component of momentum of scattered electron in y direction. It lies in the negative y direction, so I have put a minus sign here. Initially, incident photon was having none of its component in the y direction, so initial momentum was 0. So we got this equation 2, equation 3 by conservation of momentum, and this was equation 1 by energy conservation. Now we have to reach to a formula which will give us the change in wavelength of scattered photon and incident photon. So we will have to apply some mathematics here between these three equations. First of all, what you need to do is multiply this, this is equation 2 and this is equation 3. So multiply the equation 2 with C and square the whole equation. Add it with the same operation applied on equation 3. Multiplied by C and square the whole equation. When you will add these both resultant equations, you will reach to this equation number 4, which is P square C square is equals to H nu whole square plus H nu dash whole square minus 2 H nu dash cos phi. Next thing what I will discuss is this total energy of any particle in modern physics. If you want to write it in terms of rest mass and momentum of that particle, so it is written as root of m square c to the power 4 plus p square c square. Now this is total energy of electron, and this energy consists of two things. One is its rest mass energy and the another one is the kinetic energy which it possesses. So this total energy will be kinetic energy plus rest mass energy. So on squaring both the sides in this equation, you will get m square c4 plus p square c square on the left hand side, which is total energy squared, and on the right hand side a plus b whole square, you will expand it, kinetic energy whole square m square c to the power 4 plus 2 mc square kinetic energy. Now here m square c to the power 4 get cancelled. We get this fifth equation, p square c square is equals to kinetic energy whole square plus 2 mc square into kinetic energy. Now in this fifth equation, you have to substitute value of p square c square on the left hand side by equation 4. You will put this right hand side here, and the value of kinetic energy as h nu minus h nu dash from equation 1. On solving we will reach here. You will get this equation 2mc square h nu minus h nu dash. It will be equal to 2 h nu dash 1 minus cos phi. Phi is the scattering angle of photon. Okay, phi is the scattering angle of photon. Now what you have to do is divide this equation by 2h square c square. Now you will get this equation. What you have to do is cancel the h in bracket, take it common, cancel it by the h square, you will get 1h remaining in the denominator. Next we have c square in numerator, c square in denominator. Only cancel one c from the numerator, and the next c you have to multiply it in the bracket. You will get this form. And here h square will be cancelled, and you will get mu by c, nu dash by c, 1 minus cos phi, 2 gets cancelled. So we reach here. Now for light, we say that speed of light is equal to frequency times its wavelength. From here you can see lambda is c by nu, and 1 by lambda is nu by c. In this form, we will substitute it here. mc by h is equals to 1 by lambda minus 1 by lambda dash. So nu by c was substituted by 1 by lambda, nu dash by c 1 by lambda dash, and here you will have nu by c as lambda, nu dash by c lambda dash. Now solving this bracket, we will have lambda dash in denominator. In numerator we will have lambda dash minus lambda. This gets cancelled, h by mc gets cross multiplied, and you will get this formula. Lambda dash is wavelength of scattered photon, lambda is wavelength of incident photon. Wavelength of scattered photon will here in this case be greater than the wavelength of incident photon. The reason being, some part of energy of incident photon was transferred to the electron as it got scattered. So energy of scattered photon is less than that of incident photon. Hence the frequency of scattered photon is less than that of incident photon, which means that wavelength of scattered photon will be more than that of incident photon. So lambda dash minus lambda is equal to h by mc 1 minus cos phi, and this is delta lambda which we have to calculate. Here you see h by mc, it is called lambda c, which is Compton's wavelength of scattering particle. Now what's the need to define this scattering particle? In this case I have taken it to be electron, it can be any other particle also. Now this formula only depends upon mass of that scattering particle, as h is Planck's constant, c is speed of light in vacuum, both of them are constant, so it only depends upon mass. Hence we have to define this, that the Compton's wavelength of scattering particle, it only depends upon mass of scattering particle. So guys, this was for today. Thank you. Please like, share and subscribe my channel and keep watching my videos. Thank you.